Hi, we're Team 11. I'm Yasmina, and I'm presenting with Rob, Phuong, Rachel, and Jeong, and we're working on a project called rUmVa. Today, we'll be walking you through the problem we're trying to solve, our solution, our results, and our future plans. Starting with the main problem we're trying to solve, sanitation and disinfection are important to prevent the spread of infectious diseases. If pathogen-containing droplets end up on high-touch surfaces, such as desks and doorknobs, they can enter a person's system when they touch their hands to their face or mouth. These viruses and bacteria cause billions of cases of the common cold, flu, and COVID-19 annually. Many of these pathogens have all been shown to be able to live on surfaces for several days. However, it can require dozens of staff to clean and disinfect areas such as classrooms and office spaces. So these spaces are usually not disinfected daily or even weekly. In addition, the CDC recommends that when someone tests positive for COVID-19, they need to clear the area and no one can come in for 24 hours before the cleaning can begin, which costs both money and time, and puts the workers' safety at risk. If there were an autonomous robot that could come in immediately, that would be hugely beneficial. Another problem is that pathogens spread easily through the air. These particles can linger in the air from talking, coughing, or sneezing, and then are inhaled by others who get sick. Current air disinfection methods include air changes, but this requires multiple air changes per hour to be effective, and it can be disruptive and expensive to upgrade infrastructure. We met with several infectious disease experts, hospital administrators involved in safety, and competitors in the field of disinfection. And our main takeaways from our market research were that first, full autonomy is highly desired. For example, the current robot used at HUP is stationary. Second, clinical spaces have really stringent disinfection protocols. So some bacteria are really hard to kill, but they're very rarely present in non-clinical spaces. So this is why we chose to target this unmet space. And finally, there's a huge unavoidable problem related to the inconsistency of manual cleaning. Now, Jeong will walk you through our solution.
So our solution is rUmVa, which is a fully autonomous robot that is equipped with UVC lights that can intelligently sanitize open surfaces and the air in indoor spaces. This slide shows our mockup. There are three main components to our system. First, the UVC light will be used to disinfect. Second, the light will be mounted on a vertical linear actuator so that the light can extend above surfaces and avoid obstacles. And third, the robot will be fitted with an Intel LiDAR and camera sensor so that it can autonomously map and navigate its surroundings. The depth camera will be used to do three things: to detect high-touch surfaces that the robot can then focus on disinfecting, to detect humans so that the robot can shut off as a backup safety feature, and to calculate depth so that the robot knows how far away it is from a particular object. And this is a quick overview of how our design has evolved over the last 7 months. We started by assembling the rover and building the circuits to move the rover base and the actuator on top. And this semester, we worked on developing and implementing our object detection and UV algorithm, as well as autonomous navigation. We added in the UV light and laser cut housing for all of our electronics. And here are some of our key specifications. In general, we wanted our robot to be small enough to fit through aisles, have a safety mechanism, be low cost, and be easy to train. For autonomy, we want the robot to be fully autonomous and categorize 70% of the high-touch surfaces. The robot should kill 99.9% of viruses. And finally, we want to have an app with a user interface that includes cleaning records and battery life. Our robot will be running on a Linux operating system called Ubuntu, which will have the robot operating system, also known as ROS, installed. This system will be used to control all central processes. The programming language C++ will be used to control our Intel LiDAR camera, and it is used for simultaneous localization and mapping, as well as object recognition. And Arduino will be used to control the motors and wheels, the UVC light, and linear actuator in order to manipulate each part of the robot. Next, I'll hand it off to Rob.
This animation shows how the disinfection process will work. UV lamp will remain on while the rUmVa's on, and the time spent near objects will vary based on whether it's high touch or not. As the rover moves around with the UV light on, it will also be disinfecting the air around it. So as the room surfaces are disinfected, the air will be as well. This also provides another advantage over manual cleaning or just air changing ventilation. Germicidal UV light exposure, when at a sufficient dosage, has been widely proven to be effective at killing bacteria and viruses. It's also FDA approved. A question we needed to answer was, given a certain distance from an object, how long should our rover stop and provide UV light in order to fully disinfect the object and the air around it? Based on a wide range of published studies and through our own testing, we've come up with this equation. It says that based on R, which is the distance the light is from the target object, we can calculate the time needed to kill 99.9% of all COVID-19, influenza, and most other common bacteria and viruses. Now I'll tell you about our results. Here's a video of our robot in action. The robot is autonomously moving towards the table as its target. In the bottom left corner, you can also see what our robot is seeing through its camera. The UV light has not been turned on in this video purely for safety purposes. We've also started programming our rUmVa. The video shows a screen recording as I navigate through the app. First, I create an account. Then from the home page, I can click to access the cleaning records and the data interface. Finally, I can click to operate the rUmVa, and prior to turning on the device, the user also has to go through each of these safety requirements. If they don't check all of them, the app will not start the rUmVa. Once they verify that they've completed each one, the app will start the rUmVa.
We evaluate rUmVa in 4 categories: autonomous movement and object detection, virus reduction, ease of use, and safety. For autonomous movement, our LiDAR was able to generate an accurate 3D map of the room that the robot was operating in. The left picture is an angle view of the room, while the right picture is a top-down view. The neon blue line shows the robot's path to generate the map. Our object detection algorithm has an accuracy of 72.7% and has a 3% error in depth estimation. This algorithm detects high-touch surfaces such as tables and chairs for targeted cleaning. The video on the right shows the algorithm putting labels and depth measurements in real time. This graph shows how our 4-cylinder model of the UV light's intensity compared to actual measurements taken of the light. The measured data, which are the blue dots, are very close to the model predictions. This graph shows our virus reduction validation. Each horizontal line represents the necessary UV dosage to inactivate 99.9% of common pathogens, such as adenovirus, influenza, E. coli, and coronavirus. The black dots represent the UV dosage delivered by rUmVa at various distances. Every black dot is above all 3 lines, indicating that rUmVa delivers sufficient dosage to inactivate or kill 99.9% of these pathogens, regardless how far away it is. To evaluate ease of use, each team member asked 2 peers to read a provided training manual. We recorded how long it took them to go through the manual and then asked them to take a 10-question quiz about it. This is a box plot of the training assessment scores. They averaged 9.1 out of 10. This is a box plot of how long it took them to go through the training manual. They averaged 18.9 minutes. For safety mechanism, our device turns off when it detects a human, and our human recognition accuracy is 96.4%. On the left, you can see a video of the camera seeing a person and our algorithm labeling them as such. Now I'll pass it off to Rachel, who will talk to you about our cost breakdown and future plans.
So this is the cost breakdown by part type. Our rover cost us $912.01 to build. There are a couple of existing disinfecting robots on the market. They are very large in size, which limits maneuverability, and they're also very expensive, ranging from $30,000 to $125,000. Most are stationary, which requires a massive and powerful UV light to disinfect the entire room. And even when they're mobile, they're rarely autonomous and require a person to control our movements. So here's how our robot compares. Our robot fills this unmet square and is small, agile, autonomous, and inexpensive. With rUmVa, schools and offices will be able to quickly and cost-effectively disinfect spaces, keeping their students and employees healthy. This has many downstream advantages, such as fewer students missing class and performing better, schools saving money with their student health services, or companies saving money on sick leave. For further cost comparison to labor, currently, the Emergency Health and Radiation Safety Department at Penn disinfects labs twice a day. To disinfect classrooms in one Penn building, their manual labor cost works out to $20 an hour. For rUmVa, we estimate a cost of $12,500 a year, equivalent to 5 robots, which works out to $10 an hour, which is half the cost of manual labor at EHRS. Moving forward, we would like to do 3 things to improve our robot. First, we would like to transition to a mini onboard computer, such as a Raspberry Pi, so that the robot can move around with no external cables. Second, we want to replace the UVC bulb we're currently using with one of a lower wavelength in order to virtually eliminate safety risk. Lastly, we want to optimize our UV algorithm to make it more efficient and minimize cleaning time. So to conclude, we just would like to summarize the 3 main benefits of our product. First, it's effective at cleaning high-touch surfaces in air. Second, it's inexpensive compared to alternative methods. And third, it's fully autonomous. We'd like to thank the Stevenson Foundation and BE Lab and Biomakerspace and our technical mentor, Shubhranshu Mahapatra. Also, thank you to the Berkman Opportunity Fund for providing additional funds for our project. And thank you for listening.